All right, so we're going to be talking about vectors as forces. And as you know, in physics, this is a very common thing when drawing vector diagrams. Congratulations, Anna. Good job. What is a force? So a force is a push or pull on an object that changes the state of rest or uniform motion of a body. When a force such as muscular exertion is applied to an object, it causes the object to move. So examples of this are pulling up on a toboggan, lifting a book, pedaling a bicycle, or throwing a ball. So basically everything you do can be drawn with vectors as forces. Examples of this are attraction of a piece of metal to a magnet or thrust exerted by an engine when gasoline combusts in its cylinder. So because force passes both magnitude and direction, possesses both magnitude and direction, and is represented by a vector, to describe a force, we need magnitude, direction, and the point to which it is applied. So, as all of you physics people, you all know that the force of Earth is, there's a force on Earth called the force of gravity. So at the Earth's surface, gravity causes objects to accelerate at a rate of approximately 9.81 meters per second squared. So a 1 kilogram mass exerts a force of 9.8 kilograms times meter per second squared, or equivalent of 9.81 newtons. So force due to gravity is equal to mass times acceleration, or equals newtons. So this is the infamous physics equation. F is equal to m times a, or FMA, as other people say. So physics people, is this like torture to you right now? So now we're going to talk about the resultant and equilibrium forces. So the resultant of several forces is a single force that can be used to represent the combined effect of all forces acting on an object. The individual forces that make up the resultant are referred to as the components of the resultant. Single forces are vectors. The resultant of two forces is represented by the sum of the two components. So basically, it's back to vector A plus vector B is equal to the resultant vector A plus vector B. The equilibrant of a number of forces is a single force that opposes the resultant of the forces acting on an object. Okay, and now we're going to get to some examples. So these are some general examples, some visual examples. So we want to state the resultant and equilibrant of each of the following systems of forces acting on point P. So we have point P. So my resultant is going to be, my resultant vector is going to be 10 newtons west plus 22 newtons east. And because west can be considered negative east, we can say negative 10 newtons east plus 22 newtons east gives me a resultant of 12 newtons east. So the equilibrant, remember, is the number of forces, is the single force that opposes the resultant of the forces. So what would my equilibrant be? What would my equilibrant vector be? Remember, it has to be the opposite of this. So what's the opposite of east? Anybody? What's the opposite of east? West. So it would be 12 newtons west. So my resultant is 12 newtons east. My equilibrant is 12 newtons west because it opposes the resultant. Now, for the next one, we're going to do a resultant, which has to do, remember, where it's the forces acting on P. So my resultant vector, so what is the combined number of Newtons going west? What is the combined number of Newtons going west? Anybody? What's the combined number of Newtons going west? 13. We got 30 Newtons west plus 4 Newtons east, which is the same thing as saying 13 Newtons west minus 4 Newtons west, which gives me a resultant of 9 Newtons west. Okay? So can someone tell me, based off my definition of the equilibrant, what my equilibrant vector would be? Nine Newtons east. Thank you. Okay, so far, again, this is going to be pretty easy. Okay, so now we're going to go on to an example that has two forces acting at an angle of something. So find the resultant and equilibrant of two forces of 20 Newtons and 30 Newtons acting at an angle of 30 degrees to each other. So again, when I draw my diagram, this is going to be my tail. This is going to be my first force. Let's name this 20 Newtons over here. And this is going to be my next force over here, which is 30 Newtons. And in total, it acts at an angle of 30 degrees. Okay? So now I can complete my diagram. All right. So remember, my resultant is going to be 20 Newtons plus 30 Newtons, okay? And remember, my resultant always goes through the middle. My equilibrant, however, is what to my resultant? What is my equilibrant to my resultant? Are they the same or are they opposite of each other? Opposite. So where should my equilibrant lie? Outside of the parallelogram diagram or inside of the parallelogram diagram? Outside. So my equilibrant is going to be this vector over here. So that's my E. And my red one is going to be my resultant. Now, I know this angle over here that I drew is going to be 30 degrees, which means this angle at the top over here is also 30 degrees. So if you know that both those angles are 30 degrees, what is this obtuse angle over here at the top that will help me solve for the resultant? It's 150. So this is going to be 150. So because I'm solving for this triangle on the inside, I need to find the small angle theta. And my equilibrant is going to correspond to this outside angle over here, which is going to be represented by this little Greek symbol over here. So what are we going to do to find my resultant vector using this diagram? So remember, this is 20 Newtons over here, which means this is also 20 Newtons. This is 30 newtons, which means this guy up here is 30 newtons. So what are we going to do to solve for my resultant? Cosine law. Perfect. So my resultant, so R squared is equal to 20 squared plus 30 squared minus 2 times 30 times 20 times cos of 150. Okay, which gives me, when I evaluate all of this, is 2,339.23, which means that my resultant, or the magnitude of my resultant, is going to be approximately 48.37 newtons. Okay, so great. My resultant, I know, is 48.37 newtons. So what does that mean for my equilibrant vector? How many newtons is acting on that force? The same thing, 48.37 newtons, except we don't know in reference to what. All right, perfect. So we found our resultant, we found our equilibrant, they have the same number of newtons. Now what we need to do is find that tiny angle theta. So I'm going to use sine law, so I get sine theta over 30 is equal to sine of 150 over the resultant, which is 48.37. And once I take the sine inverse, I get theta is equal to 18.07 degrees. And to which vector is this relative to? Which vector is this angle relative to? Is it relative to 30 newtons or to 20 newtons? Thank you. Relative to 20 newtons. Perfect. That's my theta. However, what would my other angle be? What would my outside angle calculate to? How would I be able to find that outside angle? 180 minus theta, which is equal to 180 minus 18.07, which gives me 161.93 degrees. And that will still be relative to 20 Newton force. Okay, so my relative vector would be like this. Therefore, my relative vector is equal to approximately 48.37 newtons. That is 18.07 degrees relative to a 20 Newton force. My equilibrant is acting in the opposite direction, which means it's acting on that bigger angle that we found. Okay, that's fine. Thank you, Manru. So I got my equilibrant is equal to 48.37 newtons, which is 161.93 degrees relative to my 20 Newton force. Let's see if anyone else came late. Anyone come late? Namroop, okay, you're good. So I'm missing Mohammed and Rabbit. So is everyone good so far with these first two examples? You want it relative to 30. So you would have to find, so if you wanted to find it relative to 30 newtons, you would have, so we found our angle, which is 18.07. You would then need to take 30 subtracted from 18.07 to find the angle that's relative to 30 newtons, which is this guy right here. Okay? You can do that as well, but it's usually easier to find the inside angle or the smaller angle. So what would my angle of that green, what would the green angle measure as? If that whole angle is 30 degrees and the angle relative to 20 newtons is 18.07 degrees, what would that green angle measure then? 11.93. That's completely fine as well. I don't mind that, but it's easier to find the angle relative to the 20 Newton side because that is where we have our, that's where we have the triangle with most of the information on it. Doesn't matter, just adds more steps at the end of the day. Let's go with our next one. So now we're going to be talking about forces and equilibrium. So a system forces in a state of equilibrium when the net effect of all forces acting on the object causes no movement of the object. When the equilibrant force counteracts the resultant force, the object is in a state of equilibrium. Okay? So an example of this is the system of forces acting on an airplane. So again, all you physics people, we have lift, which is the air rushing past the wings. So this is our lift over here. That would be lift. We have the drag, which is air resistance. So if the plane's traveling that way, this is my drag. Then we have the thrust, which is the acceleration, which is going this way. So that's my thrust. And we have weight, which is the thing that's holding me down, which is the force of gravity. The thrust is counterbalanced. The thrust is counterbalancing the drag, and the lift is counterbalancing the force of gravity because they are all going in opposite directions. Okay, how many of you guys who took physics had to draw a lot of these in physics? So when three non-collinear vectors are in a state of equilibrium, these vectors are arranged in the form of a triangle, where the resultant of the two forces is opposed by the third. This means that if three forces, vector A, B, and C, are in equilibrium, such that C is the equilibrant of vector A and vector B, then negative vector C is equal to A plus B, or A plus B plus C gives me the zero vector. So in the three vectors are collinear, the sides of the triangle lie along the same straight line as in the diagram. So I have vector A and vector B going in one direction. Okay, vector A and vector B are going in one direction. However, vector C is going in the opposite direction of vector A and B. So this is going to the right, which means that vector A plus vector B plus vector C gives me the zero vector. Okay. So these are three collinear forces that give me the zero vector, and these are three non-collinear forces as well. So these guys over here make the triangle. These guys do not make a triangle at all. So let's go to a basic proof question. I want you guys to think about this for a bit. Is it possible for an object to be in a state of equilibrium when forces of 10 newtons, 20 newtons, and 40 newtons act on it? Okay. So is it possible for an object to be in a state of equilibrium when forces of 10 newtons, 20 newtons, and 40 newtons act on it? I want you guys to take a couple minutes to try to come up with a solution. And once you're done, you can type your solution in the chat or type your ideas in the chat. There are two cases to go that have to do with this solution. So if you have two different ways, feel free to share. Take 5 minutes to try to figure this one out on your own. And then type your answer in the chat once you're done. Does anyone have any guesses for this one yet? Potentially. Okay, you have the right answer for your answer. It is no, but why is it no? What is one of the reasons why it is why the answer is no? Yep. So what does that mean? It is not possible. So let's do case one. So we have to see if it's collinear and non-collinear. That's what we gotta do. So case one. So let's suppose three forces are not collinear, right? If three forces are not collinear, then they need to make a triangle. So let's arrange to see if a triangle can be formed. So let's say this is 10 newtons, this is 20 newtons, and this would be 40 newtons. We need to see if this is a possible triangle. So by the triangle inequality that we learned, I think, last week, so if you need to refer back to that in the video, you can do that as well. So by the triangle inequality, this is not possible. Since 10 plus 20 is less than 40, which means we cannot make a triangle with these three forces. Okay? Because remember, the resultant, we need negative vector c to equal to a plus b. However, 10 plus 20 is 30, which is less than 40, so we cannot make a triangle based off of that. So that is our first case. Our second case, we need to assume they are collinear. So if I have 10 newtons going this way and 20 newtons going this way, does it make sense for me to have 40 newtons going that way? It does not, because 10 plus 20 does not give me 40, okay? They have to give me the same amount of newtons back, and because they don't, it is not possible for these three forces to be in a state of equilibrium. Therefore, they will never be in a state of equilibrium. Did anyone get these answers or these explanations? Oh, I got it. Sad just gave a good joke. He's like, what's the derivative of Amazon? What is the derivative of Amazon shipping? Amazon Prime. Ha. That was actually a good one, I'm not gonna lie. Job well done. All right, so let's get into some more vectors as forces. So we're gonna have the resolution of vector into horizontal and vertical components. So if the vector f is resolved into its respective horizontal and vertical components, vector fx and vector fy, then the magnitude of vector fx is equal to the magnitude of vector f times cos theta, and the magnitude of vector fy is equal to the magnitude of vector f times sine theta. So again, we're going back to our SOHCAHTOA days. So where theta is the angle that F makes with the x-axis. So let me draw a right angle triangle. So I got my vector Fx, vector Fy, and this is my vector of my hypotenuse. Okay? So as we can see here, if we just use basic SOHCAHTOA, I know the vector Fx is equal to vector F times cos of theta, and vector Fy is equal to sine theta. So again, basic SOHCAHTOA, basic geometry, basic trigonometry. So example 4 is a snowblower is pushed with the force of 100 newtons directed along the handle, which makes an angle of 38 degrees with the ground. Determine the horizontal and vertical components of the force on the snowblower. So we got our snowblower, okay, this lovely beauty of a machine. So I need my vertical component, which is my vector Fy. I need my horizontal component, which is vector Fx. And I know the force I'm using to push on the handle of the snowblower is going to be 100 newtons, and that the angle that it makes is 38 degrees with the ground. So this is 38 degrees. So now I need to figure out what my vertical component and my horizontal component of the forces are. So based off the definition, I know my horizontal force, so vector Fx, is equal to the force that I'm applying, which is 100, multiplied by my angle, which is cos 38, which gives me approximately 78.80 newtons. Okay? And then the next one, which is my vertical force, so vector Fy, the magnitude of that is equal to 100 times sine of 38, which gives me approximately 61.57 newtons of force. Which means that, therefore, my vertical component of the force is 61.57 newtons, and the horizontal component of force is 78.80 newtons. As you can see, this is nothing too tricky, it's basic trigonometry. The last one might be a bit tricky. All right. So a traffic sign is suspended as shown. Find the tensions, so forces in the wires. Make sure to show a properly labeled vector diagram. Okay. So this is my traffic light. These are my wires. So I have a force acting up on my traffic light, but I have a force acting down on my traffic light as well. So I need to figure out how many newtons is working downwards on my traffic light. So this is going to be known as my position diagram over here, because I'm just stating the forces at which is acting on my traffic light. So if my traffic light is 10 kilograms, how many newtons is acting downwards on this traffic light? What is the force of gravity acting upon this? It's everyone's favorite number. Remember, my force is equal to what? Yep, force is equal to mass times acceleration. So my mass is 10, my acceleration is 9.81. So how many newtons of force is acting on downwards on my traffic light? Come on. What's 10? Well, what's 9.8 times 10? 98.1 newtons. Perfect. So the force acting downward is 98.1 newtons. Okay. So now let's make a vector diagram based off of this. So to create a vector diagram, I need to use that 98.1 newtons. Okay? So I have my 98.1 newtons going downwards, which means I need to figure out a triangle for this vector diagram. So let's see if we can come up with a diagram. So let's use this. Let's start over here. Continue this downwards. All right. So let's draw my parallelogram diagram. So I know these guys are 90 degrees. So now let's figure out the tension of my damn wires. So what would my tension, we need to figure out my tension of these wires. So I got tension of wire 2. Let's call this wire 2, and let's call this wire 1. Which means this is going to be my tension of vector of the first wire. So we don't have any angles, we need to figure this out. So I need to use the existing angles I have to figure out my parallelogram diagram, which is half. We need to figure out 1/2 of the triangle. So guys, so this is 30, this is 90. What would this angle of that right angle triangle be? Let's see if you guys can figure this out. $60. Thank you, Lauren. So this is going to be 60, which means if I have opposite angles, what is that red angle also going to be? The one that I just drew. Thank you for your answer. It's going to be 60 degrees. So my vector of tension of wire 2 I have is 60 degrees. Perfect. Now I need to figure out how the hell to get this angle over here and this angle over here. So we need to use the other side of the wire, which is the triangle that has to do with wire number 1. So I have another right angle triangle on my right side. What would this angle measure? $50. Which means that this angle over here is 50 degrees. Now it becomes more easier to determine my vector diagram and the missing angles. So this angle over here is 60 degrees, which means this angle over here is going to be 60 degrees. So what is this red angle over here going to measure in my vector diagram? Anyone? Let's see. This just goes to angle theorems back in grade 10. So this guy down here is going to measure 50 degrees. Okay? Which means that the tension, this angle over here, is going to give me 50 degrees. So this has to do with my tension of the first wire, which means this angle right here is going to be 70 degrees. Now, what we can do is use our sine law. So who can tell me how to find the tension of the second wire? So the tension of the second wire, so the magnitude is going to be the magnitude of T over sine 50 is equal to 98.1 divided by sine 70. I'm going to rearrange for the magnitude of the tension acting on wire 2 is equal to 98.1 times sine 50 divided by sine 70, which gives me a force tension of about 79.97 newtons. Thank you, Priyanshu. And now I can find the force of tension on the first wire. So again, it's going to be the magnitude of the first wire, or the tension of the first wire, is equal to, so magnitude of T1 divided by sine 60 is equal to 98.1 divided by sine 70, which gives me the magnitude of the tension of the first wire is equal to 98.1 times sine 60 over sine 70, which gives me a tension force of about 90.41 newtons.